Okay, in this video I'm going to be revising reactions of metals. So I'm going to start off with the reactivity series. So this is a reactivity series, or a set of reactions that you would see with metals and acids. Okay, so if you try to react metals with water and with acids, then you'll find that some of them won't react. So magnesium, zinc and copper don't react, but something like calcium will. So calcium does that and shows that it's more reactive than magnesium. When you react potassium, sodium and lithium with water, they all react, with potassium being the most reactive. It will catch fire and burn with quite a bright flame. The sodium will whiz around really quickly, and lithium will whiz much slower. Okay, the sodium will pop and fizz and produce a lot of hydrogen. So all three of them will produce hydrogen, but potassium being the most violent in reaction, followed by sodium. That tells us that potassium is more reactive than either sodium or lithium, and trying to react them with acid is too dangerous. Then if you react these less reactive metals with acid, magnesium will react, zinc will react slowly, producing a few bubbles of hydrogen, and copper will not react. Now, the reactivity series, as an idea, is all of the metals can be put in order of reactivity by seeing which is the most reactive and which is the least. And then that's important when we come to things like displacement. So when you react a metal with water, hydrogen is given off. The other product is a metal hydroxide. So you could have calcium hydroxide, or you could have lithium hydroxide, or something like that. But a metal hydroxide is also known as an alkali. So that's why group 1 metals that react with water are known as the alkali metals. So you produce this metal hydroxide and hydrogen. Okay, so if we looked at all of those reactions, we can use this standard reaction here. Okay, the metal plus water makes metal hydroxide and hydrogen. You can use that to predict all of the other reactions. So sodium and water would give metal hydroxide. Okay, so that would be sodium hydroxide, sodium's the metal, and hydrogen gas. So hopefully you can predict what the rest would give. So you'd have potassium hydroxide and hydrogen, calcium hydroxide and hydrogen, and zinc hydroxide and hydrogen. So they're all producing this metal hydroxide and hydrogen. So it's really important going into your exam that you know these common general formulas, like metal plus water makes metal hydroxide and hydrogen. So if you're doing higher tier, then you should know that what's happening in there is the ions are being formed. I'll go into this in a little bit more detail, but I've got the reaction here of sodium with hydrochloric acid. So as you can look at or try and get some understanding of what we've got going on here. So when you react sodium with hydrochloric acid, the sodium will form an ion. It will produce hydrogen, so it will displace the hydrogen from the acid, and then it will then accompany the chlorine. So it's displacing the hydrogen to form sodium chloride. So the hydrogen in the hydrochloric acid starts off as an ion, and then it ends up not ionic. Okay, so it would be a covalent bond, it would be a simple molecule. So the hydrogen has gained electrons, so it starts off as a positive ion and then it gains electrons. Now the fact that sodium reacts more readily than magnesium is down to the fact that it will form the ions more easily than magnesium, and that's to do with its electronic structure. But then that also means that we can put it higher up in the reactivity series. So there's a similar reaction for magnesium. Okay, so it forms this salt. Okay, so it's forming magnesium sulfate and hydrogen. So this is metal and acid makes salt and hydrogen. Okay, so pretty similar to metal and water will make metal hydroxide and hydrogen. We've got metal and acid make salt and hydrogen. So if you put some compounds, okay, ionic solutions in different spotting tiles, then you can do a displacement reaction by putting different strips or pieces of pure metals in and seeing where there'll be a displacement reaction. Now, a common one is to put something like copper sulfate in with zinc or iron. So the iron, you could just use a small nail, and the iron nail will get coated in copper as it displaces copper from the solution. So in the solution, the iron will dissolve as it's reacting and forming iron sulfate. We call that a displacement reaction. So when we do this with a group of different solutions and metals, then we can also form a reactivity series here by seeing that magnesium is the most reactive because it will do 3 reactions compared to zinc only doing 2 reactions. So we've got magnesium sulfate reacting or not reacting with anything because the magnesium won't displace itself, okay, and it can't be displaced by zinc or iron or copper. But if we look at zinc sulfate, the zinc can be displaced by the magnesium because the magnesium is more reactive than the zinc. So these are all solutions, and these are all just pure metals that are being put in to see what can be displaced. Now, some of the reactions can be quite violent. I've got a picture of a thermite reaction here. So the thermite reaction is when you react aluminium with iron oxide. The two of them are powders, and so the aluminium will displace the iron from iron oxide, leaving aluminium oxide and iron. And it's a very violent reaction, very, very exothermic. And because you can react them both as powders, you've got a really high surface area, and so you get a really high rate of reaction. Now then, when we look at the reactivity series is quite useful when you add a couple of non-metals to it. So you can add carbon and hydrogen to the reactivity series. And these are useful because you can find them in quite common forms. So carbon in quite a common pure form is coal. And then hydrogen is found in acids and in water. So all of these low down metals, these metals from low in the reactivity series, will not react with acid because they won't displace hydrogen from its compound as part of an acid. Now, carbon here being coal will displace anything that's below it. It might need to be heated to encourage the reaction to take place, but it will displace them. But it can't be used to displace anything like aluminium, magnesium, calcium, sodium or potassium because they're too reactive. So the carbon will react and it will displace, say for example, oxygen from iron oxide to create carbon dioxide and leave pure iron. Now that's a particularly useful reaction for extracting a metal from an ore. So I've just got a duplicate of that slide there. So a displacement reaction is one where a more reactive metal will displace a less reactive metal from a compound. So just as another example, if we react magnesium with copper sulfate, because the magnesium is more reactive than the copper, it displaces the copper from copper sulfate. Okay, so essentially it's like it's stealing the sulfate for itself, okay, and pushing the copper out, so the copper is by itself at the end there. So magnesium and copper sulfate would make magnesium sulfate and copper. Okay, so it's just a displacement reaction, and it's another way of seeing which is the most reactive of two metals and forming a reactivity series. Now I talked about ores. Ores are just rocks which contain enough metal to make them economic to extract. So unreactive metals might be found in the native state, which is just them as elements pure in the ground, so like gold. And then others are typically found as oxides, and then they need to be extracted with carbon if they're less reactive than carbon, or using electrolysis if they're more reactive than carbon. So anything that is less reactive than carbon can be displaced using carbon. These down here are typically found in native form, and then anything that's more reactive would need to be displaced using electrolysis. Now in this case you'd get something like lead oxide being reduced, and a simple understanding of reduction is the loss of oxygen, and then oxidation is the gain of oxygen. And we can look at reduction and oxidation in terms of electrons, but you can also look at it at a simple level in terms of oxygen. Now if we look at this, okay, copper itself is losing its oxygen, so we say it's being oxidized. Sorry, it's being reduced, so it's losing its oxygen. So the copper, as it goes from copper oxide to copper, is reduced. And then the carbon, which starts off pure as an element, gains the oxygen, so it's being oxidized. Now, from these two solids that are reacting, we create a solid and a gas. Okay, so carbon dioxide, when it's produced, it's going to carry away some of the mass. So it might seem like the mass is decreasing, but obviously because you're not creating or destroying atoms, you should realize that the carbon dioxide is just being carried away. That's where it's really useful to be able to look at the state symbols to predict what you might be able to see when a reaction is happening. Now, at a higher level, you need to be able to consider oxidation and reduction as the gain of oxidation being the loss of electrons and reduction the gain of electrons. So oxidation is loss and reduction is gain of electrons. So we could look at copper here, okay, and we can say the copper is positive because it has not quite enough electrons to match the number of protons, and then it gains electrons, so it's being reduced. Okay, that's a bit confusing. It's gaining something, but it's being reduced, but that's just the terminology. Okay, so reduction is gain, so it's gain of electrons, and it becomes pure copper. Now, if a metal is less reactive than carbon, it can be removed from its ore using carbon, and that's an example of a reduction reaction. So something like iron oxide and carbon would create iron and carbon dioxide, or copper oxide and carbon would create copper and carbon dioxide. The idea is the carbon is displacing the oxygen from the compound. So metals that are more reactive than carbon can be extracted using electrolysis. It's very expensive, but it's the only way that you can do it. So you can use aluminium to extract it. So electrolysis literally just means breaking down using electricity, and it's done in an electrolysis cell. Now it's important because you need the movement of ions that there is a liquid in here, and we call that liquid the electrolyte. So this electrolyte is aqueous copper chloride, but you could use a molten solution as well. Now I'll talk a little bit more about electrolysis in a bit, because electrolysis, when you have solutions, can be a little bit difficult and a little bit complicated. This is quite a simple one because it's just copper chloride. So we've got copper ions. They would be positive. They would be attracted towards the negative electrode. So the cathode is the negative electrode. I always think of cats being negative, so I think cathode. Right, cat, that's the negative one. Doesn't matter if it doesn't make sense, it just helps me to remember it. So that's negative because that's where all of the electrons are, and then the anode is positive because all of the electrons are moving away from there. So the positive is where the negative ions will be attracted towards. So chlorine, being a negative ion, will be attractive to the anode, and copper will be attracted to the cathode. So, in that case, we've got at the cathode, copper gaining electrons, so it's being reduced. Reduction is gain, okay? And chlorine is being oxidized. Oxidation is loss. So it's negative, it loses its electrons, and it then forms chlorine gas. Difficult to think of oxidation as having happened because there's no oxygen involved in this reaction at all. But in terms of terminology, it's still an oxidation reaction. It's still a reduction reaction happening as well. So a redox reaction is when the two reactions happen simultaneously. So we've got a redox reaction, which is reduction and oxidation. Now moving on to metals with acids. When you react a metal with an acid, you create a salt. Now, the name of the salt will have the name of the metal in and part of the name of the acid in. So nitrates here come from nitric acid, and sulfates come from sulfuric acid. So hopefully you can think of what a hydrochloric acid would form. So hopefully you've got it in your head. Hydrochloric acid forms chlorides. So hydrochloric acid forms a chloride. It's got chlorine in it. Okay, so it's chloride. The rest are called ates. So rather than chloride, it's nitrate and sulfate. Do you know why? Hopefully by now you do. The term, when you've got ate in the name, it shows that there's also oxygen in the compound. So a nitrate has nitrogen and oxygen and whatever metal in there. So for example, sodium nitrate, sodium, nitrogen, oxygen. So my examples I've got here are magnesium chloride. Okay, so that's when you react magnesium with hydrochloric acid. Calcium nitrate would be formed with reacting calcium with nitric acid. And zinc sulfate would form when you react zinc. Now, zinc sulfate could be formed with reacting it with sulfuric acid, but it's not just metals that can be reacted with acids to produce a salt. You can also react metal hydroxides or alkalis, okay, where you can react metal oxides, okay, like zinc oxide. So that would be called a base. So a base is something that can neutralize an acid, and if it's a soluble base, it's an alkali. So the hydroxides, like lithium hydroxide, they dissolve, so they're soluble, so you call them alkalis. But if it's insoluble, like copper oxide, it won't dissolve, okay, but it will still react with an acid to form a salt. You can also react metal carbonates, like copper carbonate or lead carbonate or any metal carbonate with an acid to form a salt. So when you react a carbonate with an acid, you also produce carbon dioxide. So I said in the carbonate, because it has 8 in it, it's got some oxygen in it. So some of that oxygen with the carbon will go into carbon dioxide, and some of the oxygen will go with the hydrogen from the acid to make water. And then what's left over is the chloride bit of hydrochloric acid and the magnesium from the metal carbonate. So you've got your salt, which is just magnesium chloride, and water and carbon dioxide. So it's important that you know that the general formula for metal carbonate and acid is they react together to produce a salt and water and carbon dioxide. So just like these, hopefully you could predict, if you pause the video, what would be formed in each of these. So calcium carbonate reacting with hydrochloric acid would produce calcium chloride, it would produce carbon dioxide, and it would produce water. Okay? Hopefully you can pause the video now and see if you can complete those. So here they are completed. Okay, so all of the reactions are now complete. It just forms the metal and the name of the acid going together to make the salt, carbon dioxide and water. Okay, now if I'd have had oxides rather than carbonates, I wouldn't have produced the calcium, the carbon dioxide. Okay, I would have just produced water. If I'd have had hydroxides, I would still have produced water, and I wouldn't have produced the carbon dioxide. So just a little recap then, okay? A lot of these reactions are redox reactions, okay? We have both oxidation and reduction happening at the same time. And oxidation is loss of electrons and reduction is gain of electrons. Now then, when you look at something like this, you've got magnesium and sulfuric acid reacting together. Now if I include the state symbols, we've got magnesium and sulfuric acid making magnesium sulfate and hydrogen. Okay, my formatting's gone a bit off here, so some of this has, some of my state symbols have moved a little bit. Let's see if I can sort that out. So, no, definitely not rubbing out for me. So, the aqueous is the acid. The salt is also aqueous, so it's just dissolved in water. And then the hydrogen gas is produced. So hopefully you understand and appreciate the fact that the gas, you're going to see the gas coming off. Okay, and then this is higher tier then, that you could also complete and say what the ions are. Okay, so magnesium, okay, is not ionic. Okay, so it's just going to be magnesium. Here we've got a H plus ion, and here we've got a SO4 2 minus ion. So we've got two of those H pluses, and then that's going to react and produce Mg2 plus, the SO4 2 minus, and the H2. Now I'm going to cancel that out because that's common to both. So I could just say that Mg and 2H plus is going to react to give me Mg 2 plus plus H2. Now what's happening here, what I'm doing is I'm looking at what's being reduced and what's being oxidized. Now the sulfide ion stays the same, so is unchanged in reaction. So I'm going to use a little bit more space down here. The magnesium, when it forms Mg2 plus, is giving up 2 electrons. So it's losing electrons. So I think oil rig, oxidation is loss, it's being oxidized. And then the 2 hydrogen ions are going to gain those 2 electrons to form H2. So it's gaining, it's being reduced. Okay, gaining electrons, being reduced. Okay, so we've got little ionic half equations there. So that's quite a difficult little skill. I'm going to flick forward. Okay, if you're watching this video and you fancy giving them a go, try the one with hydrochloric acid and sodium hydroxide, and I'll put the answer up in a second, and I'll go through a couple more, put the answers up, and then if you want to pause the video and give them a go, you can. So this shows what's being reduced and what's being oxidized. Okay, so another little example here. So these are being completed. That's the ionic equations. And then here's some useful little ideas moving forwards. So a base is a substance that will neutralize an acid. An alkali is a type of base that's soluble. So soluble hydroxides are alkalis, like sodium hydroxide or lithium hydroxide. And acids produce hydrogen ions in an aqueous solution. Okay, alkalis produce OH minus ions, so hydroxide ions, in aqueous solution, and the hydroxide ions then are what are going to react with the hydrogen to form water. Sorry for that pause, just a little short break, somebody had a question. So it's important that you can appreciate those things, okay? Key ideas. Now overall, when you neutralize an acid, it's because two things are reacting and forming something neutral. So salts are neutral, okay? So if you form a salt and some water, because water is also neutral, you're neutralizing. Now the salt is neutral, but the salt really isn't that changed because something like the chloride ions in hydrochloric acid are going to react with the metal ions, and there's not a huge amount of change there. So they don't really change the ions, but what does change is if you've got something like hydrogen and a hydroxide reacting together, they are reacting forming a new compound, okay, that is different, its structure is different, and so that really is where the new product is being formed that makes it a chemical reaction. So hydrogen ions and hydroxide ions could be dissolved in some water, okay, so we're talking about solutions that are reacting, so the solution means there's already some water there, but it forms more water, okay, so that water is neutral, and that's what makes it a neutralization reaction. So acids produce H plus ions, and alkalis produce OH minus ions, okay, and those will react together and just form H2O. They'll be attracted to each other because they're opposite charges, and then there'll be a redox reaction in terms of what's happening to the electrons, and it forms this neutral water. Now I'm going to just quickly go through the difference between concentrated, dilute, strong and weak acids. So I've got a bit of a contrast here. Okay, I've got a dilute solution here, and this dilute solution is dilute. Okay, the red represents something like water. Okay, and the blue represents the thing that's dissolved in the solution. Now it could be water, it could be ethanol, it could be any sort of solvent, okay? But this is dilute because there's very few blue in the red. Okay? Here we've got the same reds, but a lot more blue dissolved in it. Okay? Now when you're calculating concentration, you use the formula moles or amount, okay? It could be moles or it could be amount in grams, divided by volume, and your volume is typically in decimeters cubed. Okay, so moles per decimeter cubed, or occasionally grams per decimeter cubed, but I prefer to to think about molar solutions, so mole per decimeter cubed. Okay, so more moles dissolved in the same volume gives you a more concentrated solution. Now, here is the difference between a strong acid and a weak acid. Now, we've got the same concentrations, they both dilute, okay? But when we look at the strong acid, it's strong because what happens is it's dissociating. So the H plus ions are separating from the A, which is the other part. So the A is representing like an unknown. It could be chloride, it could be sulfate, it could be nitrate. And so the strong acid is strong because it has so many of these hydrogen ions in a particular concentration. So the higher the concentration of hydrogen ions, the stronger the acid, the more likely there is for there to be a successful collision between a hydrogen ion and something else. Okay, so like it could be a metal, it could be something else in solution. Whereas a weak acid, like citric acid or ethanoic acid, only partially dissociates. So these have stayed as they were, HA. Okay, and this is dissociated to H plus, the acid component, and then the other part. Okay, so something like ethanoic acid will split into this H plus, and then the rest of the ethanoic bit. Okay, which is a nasty little formula. So we've got the nasty little formula here. Okay, so this is the ethanoic acid, and it dissociates to form this and the acid. It's a reversible reaction, so it happens both ways. Whereas this is not a reversible reaction. It happens and then they're dissolved in solution and they're happy as they are and they don't go back. Now, another example of a weak base, okay, so think alkali. It's not actually an alkali, it's a base. But we've got this one here is ammonia dissolved in water. Okay, so this alkali will form NH plus, and then this OH minus, which is what makes something alkaline. Okay, again, it's a reversible reaction, as is this. So there's always some NH3s and some NH4 pluses, some OH minus, so some hydroxide ions, some alkali ions, and in this case up here we've got some hydrogen ions. I really hope that you can see my clicker and my pointer, otherwise I'm just talking about random stuff. Now these are both more concentrated. They're more concentrated because there is more of them in a volume. And you could imagine that the rest of that volume is filled with water. It's more concentrated because there's more per volume. But if you look, there's still only a couple of acid ions here, okay? Or hydrogen ions that make the acid, whereas there's loads here. So this would have a much lower pH than this one. So the weak acid, okay, although it could be the same concentration, will have a different pH to the strong acid of the same concentration. So that's that summarized. So when the H is separated from the A, it's a strong acid, and when they're together, it's a weak acid. The amount of a substance in a certain volume is called a concentration. So strong acids are fully ionized, but weak acids are only partly ionized in solution. So that is the end of metals and their reactions. Okay, it's a big component supposedly of this reaction, not this reaction, this exam that's coming up. There's a couple of key required practicals. Nobody does the required practicals better than Malvern College, Marlborough College. So if you just search up the required practicals, okay, they're going to come up top on YouTube. I just wanted to do a little video that went through everything, okay? I hope it's been useful, okay? Maybe more than one person will watch it, maybe less, who knows? Okay, but it's a whole module covered in an hour, so it's worthwhile time if you've watched it. Thank you for watching. And I guess now I should say don't forget to like, comment and subscribe, but I'll probably turn comments off, so just, subscribe, and bye for now.